Welcome to Terrible Lizards, a podcast about dinosaurs with Dr. David Home and Izzy Lawrence. On this week's episode, Dinosaur Evolution, who is related to who and how we work it out. Also, Professor Sophie Scott wants to know what noises dinosaurs made. Welcome to episode 7 of Terrible Lizards. Now, this one was voted for by our lovely, shiny, sparkly patrons on Patreon. If you join us on Patreon, you will be able to get little things like being able to vote for what topics we cover. I know. And they had 4 choices, Dave, okay? They had how scientific papers to get published, dinosaur evolutionary relationships, and theropod feeding patterns. Now, I thought it'd be nommy theropods going, arr, arr, arr. But
yeah, I did.
That only got 6 votes.
Third. Rubbish.
Third, indeed. Well, yeah, how scientific papers get published. I mean, send. That must be it.
I didn't think people would be that interested in it, but I picked it because I think it's really important that people understand how we do science. But I thought it might accumulate more than...
It got 3 votes.
It got 3?
Yeah,
Okay.
it got 3 votes. So there are at least 3 nerds among our patrons. And the people who voted for that, you are Dave's favourite people. It is between dinosaur evolutionary relationships and the strangest sauropods. And now, personally, I am shocked because I thought the strangest sauropods would be able to talk about, was it Eorapasaurus or something like that?
Yeah, Nisiosaurus and Mamenchisaurus and
all the weird Titanosaurs and it'd be so cool. But no, we're not going to do that. We're not going to do that. We'll do that in a later series. We're today going to talk about dinosaur evolutionary relationships, which is when dinosaurs get all kissy in an evolutionary type way. I have no idea. So what are we... What do you mean by this? Isn't this just, how they evolved? Haven't we covered that?
Well, ultimately it is, but we've talked about, X group is close to Y, dromaeosaurs and troodontids are very close to each other and they're very close to birds, and actually we can't always tell. But, where does that information come from? When I get to say that with confidence, why do I know that, or how do scientists work that out? And that's really what I wanted to cover, and what was in my mind when I picked that as a topic.
Okay.
Because we definitely haven't talked about that at all.
Where do you want to start with this? We could talk about pelvises. I know that's important. And the fact that the theropods come from the lizard type of pelvis, which isn't the ornithischian type of pelvis, even though the ornithischians have got nothing to do with birds, and the theropods developed an ornithischian type of pelvis from a lizard bird.
Very good. Yes.
It hurts.
Yes, all correct, but... that's part of it. But I think actually we covered this a bit in the last episode when we talked about, species and how we name species and how we identify them. And I talked about, identifying characteristics which will tell you what group they're in or how similar and different they are from any other specimen. And that's really what we're doing with evolutionary relationships, just writ very, very large indeed.
Okay.
We'll try and pitch this to the mind of Izzy. So you have cats, right?
I have 2 cats.
You have 2 cats, and we all know what cats look like.
Yes. Cute.
Right.
And angry.
Okay, right. So, is a leopard a cat?
I would argue that a leopard is a big cat.
So, right, a leopard, you are happy that a leopard is a type of cat?
Yeah.
Right, and what about a fox? Is that a cat?
I would argue that no, which is annoying because it should be.
Right. Okay. Why is a leopard a cat and a fox not a cat?
Retractable claws!
Right, but some badgers have retractable claws as well.
And some, cheetahs don't.
Don't, right.
Oh, cardboard box. If you put a cardboard box down...
yes, leopards and jaguars and other things will sit in boxes. And yes, I've seen the videos.
I don't think foxes will.
But that's ultimately what we're getting at. We all kind of know this. I can show you a picture of a type of canid that you've never seen before, and you'd go, well, that looks like a fox or a dog, and it's not a cat or a hyena or a bear. So that's what we do. We are trying to quantify and codify those kinds of differences. And we're doing that at a very large scale. So big analyses now in paleontology might have, a couple of thousand individual discrete characters, so discrete little anatomical features coded for every single species that they're analysing. And there might be a couple of hundred of them. So tens of thousands of data points. And these can be general characters. Does it have a proportionally large head? How many teeth does it have? Does it have serrated teeth? How large are those serrations? Are those serrations appear on every single tooth? Do those serrations just go down the front and back, or just down the front, or just down the back, or both? Do they change shape or size at any point? And on and on and on and on and on. And that's what we're doing. And we're scoring, as I say, tens of thousands of these. Yes, this tooth has it. No, that animal doesn't. That tooth is missing, so we don't know. So usually, traditionally, we write a question mark, or occasionally it's highly variable. Sometimes you see them with one, sometimes you see them without. Humans with wisdom teeth. Some people have them, some people don't, some people have lots. So
lots, do they?
Some people have extra. So you wouldn't want to put one number in there to represent that. You'd want to represent the variation. And then we're sticking that in a computer. I learnt to do this back in 1998 by hand. I was taught to do this by hand on a much, much smaller data set, I should say. Was
this Fortran programming, perchance? Did you use Fortran for this? Just out of interest? No? Okay, fair enough. I wonder, cause I'm one of a sort of select group of sort of undergraduates who were trained on this particular type of multivariate statistical stuff, which only is used then, and it never is used ever again.
Yeah. No, the few years between us, I believe, saved me from that. And then we're sticking it in a computer. And what the computer is basically doing, and this is a simplified version, and I should say this is one of multiple methods of doing this, but what it's basically doing is finding the things that have the most in common. And we're making an assumption, and actually a very reasonable one, which is backed by a hell of a lot of data, but we're making an assumption that the things with the most in common are very close, or the most closely related things to each other, and things that have less in common are a bit less closely related to each other.
You've got to be careful with that, because you've got things like, parrots have beaks, and octopus have beaks, and triceratops have...
Right, we've already had that with retractable claws. So there's two ways that we're effectively getting around that. First of all, we're looking at features in detail. So one that I used to teach my students, which is relevant to us because we've done Spinosaurus this year. Spinosaurus has long nose, and crocodiles have long nose, and there's an extinct group of Triassic semi-aquatic reptiles which are very crocodile-like in a way called Phytosaurs, and Phytosaurs had a long nose, but they all did it in different ways. Phytosaurs, basically one group elongated, so in terms of the snout, you've got the premaxilla at the front and then the maxilla behind. And one group just made the premaxilla really long, and one group just made the maxilla really long, and one group made both of them longer than normal. So if you just coded your character as long nose, you would think that all three of them were very closely related to each other. But if you convert that into long and short premaxilla and long and short maxilla, you will soon see that they're different. So that's one way we can get around problems of similarity, convergent. The other way is we just swamp it with data. Because yes, parrots and Protoceratops actually have really quite similar beaks, but they have a hell of a lot fewer features in common than they do. They have a hell of a lot more features that separate them than put them together. And on average, data sets will show you much more evolutionary history that's genuine than occasional convergences.
Just out of interest, because this requires you to have built the data set and then sort of see what correlates and what doesn't. When was these data sets first built? Because presumably we're talking like 1970s, are we? Or
66, famously. So it was a German entomologist called Willy Hennig.
Of course it was a German.
Well, interesting thing is like Hennig was trying to come up with a method that he wanted to be as objective as possible, though of course it still inevitably has a lot of subjectivity to it, but it is as objective as possible for codifying evolutionary relationships. That's what he was trying to do. He wrote a book in 66 and it got translated into English, I think in 1970, something like that, and it was still basically ignored by everyone. And the first group of people to pick it up, ironically, were not evolutionary biologists, but linguists. So when people talk about languages and how words move around and which words and languages are descended from others, that's using Hennig's methods. That's they were the first group to pick it up. But it kind of took off, I want to say, in kind of the 90s. It finally got going. And part of the problem was data set. So yeah, I learnt to do this in 97, 98. And at that time, a computer could run an analysis with maybe 8 or 9 species or groups and 40 or 50 characters. And anything more than that, particularly number of groups, it really started running into... Like, you'd be waiting days for the results. And which is why I learned to do it by hand.
Oh, Grandpa.
But it also meant that it also meant that people, even if you wanted to apply his method, you knew you were doing it in a very superficial manner. And then by the time I did my PhD graduated 2005, handed it in 2004. So 7 years later, I was running an analysis on an iMac, if you remember those, the little coloured ones that you used to have. And I had, I want to say, something like 50 taxa and a couple of hundred characters, and it was running it in a few seconds.
Nice.
So, it's that classic computational curve of doubles every few years, going absolutely through the roof. And even then, I'd been working on a program which took about 2 weeks to resolve my analysis. And just before I finished, this new one came out, which did it in 2 seconds. And I was like, I wish I'd had that 18 months ago. Because that's the thing, because you'd spot an error or you'd get a weird result or you wanted to change something up and go, but what would happen if I did this instead? And then wait 2 weeks for the answer.
Oh, wow. Occasionally, you know how you have to update your software overnight? That's the longest wait. Oh, my goodness. How did we cope? Well, precisely. And now we have all kinds of complicated models that are making predictions for missing gaps, and we can So when I did it, it was all binary. It was all, it has this or it doesn't have this. Or occasionally you would have like short, medium, long, very long. So you'd have 0, 1, 2, 3, 4. Now we've got systems where we can plug in raw numbers. You can measure the length and then just put the length in. You've got actual numbers and you're not trying to artificially split it up into bits that you've predicted or worked out you think are relevant. And the thing is that what that does is it allows you as well to look at the numbers themselves, which is really important. I'm a bit of nerdy when it comes to statistics as well. I was working on a thing. We basically had to work out whether there was a particular pollutant in a city. And we were doing this through birth weights. So this was, they were burning stuff at the hospital, and everything downwind of this, the birth weights, every child pretty much was underweight in this particular sort of like wind corridor. And so from the data, you looked at the data, the thing went, and like literally it was like obvious. There's a huge correlation. This was dangerous. And then you actually looked at the raw data and you saw, hang on, some of these babies are 200 grams. That doesn't make any sense. 200-gram baby, that's a bit too little.
Yeah, that's an orange. That's...
Exactly. Yeah. What's going on here? And then we got the map of where the nurses worked in the nurses' district, the people who came round to weigh the babies. And all of the bad data was from this one particular nurse. Who couldn't... So actually, this thing was fine. The reason I'm saying this is it's really the more data you can actually put in, actually goes to show, actually, we've got a paleontologist who can't use a ruler here. So... Yeah,
raw data's really nice.
It's good.
It can be... It's a double-edged sword, though, because you've got to remember with paleontology, so many things are broken. I could have a long-nosed animal that is very obviously long-nosed, but if you want the total measurement, the end's missing, and I don't know what that is. And you don't want to throw out data because data's valuable. And so we do run into problems with paleo that we don't with other fields. And of course, we're not, we don't have muscles, we don't have brain, or even if we do, it's like, brain case. We've talked about brain cases. You can code all kinds of different things about the brain, but they're really few and far between. So, doing a big analysis and going, I've coded my 3 brain cases and it's like 1 deer and 1 primate and 1 rat. It's like, that's really not going to help us work out the evolutionary relationships. We're just adding a massive data and doing a ton of work which would make no difference to anything.
So how are you working out, animals, who came first and who came last? Is it a case that they go away from entropy or towards entropy? Do they get more complex or more simple?
So we use what are called outgroups. And outgroups is something that you are very confident is not part of your group that you're interested in, but is still very close to it and therefore has an awful lot of features in common. So for dinosaurs, we'd use things like crocodiles. We're very confident that crocodiles are very close to dinosaurs. They're both archosaurs, particularly the fossil crocs have a whole bunch of things in common with them. We can see all those features, we can measure them confidently, but we're really pretty sure we're not mixed up and accidentally included a weirdly crocodile-like dinosaur in our data set. And that gives us basically a degree of polarity. An interesting aside, which is really nice, is that if you look at the family trees that we produce, so this is the source of those big family trees that you will often see, and they're correctly called phylogenies. If you look at a phylogeny and look at where things appear and where the branches are, and if you line that up with the fossil record, there's a really strong statistical correlation. So in other words, the things that we think evolved later appear later, and the things that we think evolved first actually appear earlier. There's obviously loads and loads of exceptions, but on average, it's a very tight correlation, which gives us a very good sense that our analysis is actually right.
So all you need to do is sort of like find a rabbit in the late Triassic and cry for a week.
You're a smidge off a famous quote about evolution. JBS Haldane, famous evolutionary biologist, he's the source of two very famous quotes, which I teach my first years because they're so common. One of which is he was once asked, what, if anything, would diversity or biology tell us about the mind of a creator? And he said, they would have an inordinate fondness for beetles. Because diversity of beetles is, I think, of named animals, so not including bacteria and smaller stuff. Insects are something like about 60-70%, and of them about a third of beetles. There's an awful lot of beetles out there. And you will see this in museum after museum after museum. Almost every natural history museum now will have a cabinet with the line, an inordinate fondness of beetles, and then hundreds of beetles pinned underneath it, show just how many there are. So Haldane's responsible for that one. And the other one he's responsible for is he was asked, what would convince you that we've got evolution wrong? And his answer was a Precambrian rabbit.
Oh, there we go.
So you
picked the right animal.
You're a few 100 million years off, but and that's what he's getting at. We would have to have misunderstood the fossil record and evolutionary history and diversity so unbelievably wrong to get a rabbit that first appears, actually, I don't know how far rabbits go back. Certainly not into the Mesozoic.
I mean, in Britain, the Romans brought them over.
Yeah, but rabbits as a clade, we'll call it 50 million years old, and we found them 500 million years ago. It's like, that's how wrong we'd have to be.
What's freaky about this is obviously there must be a reason why I picked that, and obviously I've read it somewhere, and I have no memory. That's scary.
I did wonder, because, you could have picked anything and you picked a rabbit.
Well, I'm the sort of person who reads New Scientist, so like 10, 20 years ago when I was reading it, and saw... Oh, that's freaky.
But Precambrian rabbit is like this little phrase in biology. But, again, this is paleontology, and this is dinosaurs, and we have some big issues. So there's tons and tons and tons of information in the skull. There's loads of bones in the skull. There's all your teeth. It's the brain case. It's really important for, huge amounts of what you do. It's got your senses in it. It's got your feeding apparatus in it. Sauropods, we have like 15, 20 good skulls in total for that whole group, and several of them are for one species. So the thing with the most information in it, we don't have. And then with sauropods again, they've got these lovely big solid limb bones that we find all the time. But they're weirdly simplified in sauropods. So actually there's not a huge amount of data in them. And the lovely, amazing architecture of their vertebrae, because of all these pneumatic gaps and spaces in them, just get crushed and folded and mangled. So for sauropods, we don't have skulls, which would be like half the data in any other data set. We do have the limbs, but they have less information than almost any other data set, and the vertebrae are generally mangled. So oddly enough, our understanding of sauropod relationships is not very good compared to a lot of the other groups.
And I still can't get over the fact that sauropods are more closely related to theropods than the ornithischians, and that just really upsets my brain.
Unless they're not. So this
is...
Yes. Well, first of all, you've got to remember that, that's the issue with evolution, and this is why the fossil record is so important, even for working out the relationships of modern living species. So, we look at elephants and go, actually, the nearest relatives of living elephants are things like hyraxes, which are these little fat, fluffy rat-like things, and manatees and dugongs. And that looks insane unless you start looking at their fossils.
Whales are even weirder.
Yeah, because they're effectively related to hippos. Well, they are related to hippos, but again, if you go back into their ancestry, it becomes a hell of a lot more obvious. And yeah, ancestral early sauropodomorphs are human-sized and don't have giant long necks and are running around on their back legs. And suddenly you see that gap between Brachiosaurus and a velociraptor has been reduced somewhat. But there's a fundamental. The further you go back in time, generally the fossil record is less good. There's been more opportunities for the fossils to be lost, basically. And also, the further you go back in time and the closer you get to the origin of a group, those things are going to be more similar to each other. They haven't had tens of million years to separate out and diverge and look different. And so inevitably, the origins of even very major groups are often very hard to discern from each other. And even though we've always said on the pod, and indeed this has been kind of dinosaur orthodoxy for 120 odd years or whatever, that you've got the theropods and the sauropodomorphs and they form the Sauricians, and then you have the ornithischians on the side. That may not be right. So there was a paper came out, I want to say about 2016, 2017, with a big new analysis of lots of these early dinosaurs and lots of their ancestors. So we think we mentioned before these dinosaur morphs and dinosaur forms and coelosaurids and these other things.
I remember them.
Yes. And stuff which we now know is relatively close to the pterosaurs. So big analysis of all this early stuff. And the analysis suggested that actually the ornithischians are closer to the theropods and the sauropods, or the sauropodomorphs, are the separate ones.
From an outside perspective, looking at your toys, it looks like the ankylosaurs and the ceratopia, pretty much the same thing, stegosaurs and that sort of bracket.
Short, fat quadrupeds.
Exactly, short, fat quadrupeds. And then you could kind of see a few of them getting bigger and growing a long neck and becoming sauropods. That kind of, makes sense, even though sauropods are really earlier, aren't they?
That's another division again. So inevitably, things come round again. In the early days of dinosaur science, we had these three groups and no one quite knew how they were related to each other. And so people have inevitably proposed all three combinations, if you like. So the sauropod and theropod would be the Sauricia, and it's the one we use, and it's the one we've stuck to for convention. Though I think on balance it's probably still right, but it's not like 99-1. It's kind of like 55-45 probably at this point. But that's what we're sticking to, because that's what every single book and every single exhibition will say at its easiest. Then we've got the idea that the ornithischians go with the theropods, and that group is called Ornithoscelida. But then there's also an idea that it's the sauropods that go with the ornithischians, and they're called Phytodinosauria, so the plant dinosaurs, because it's basically all the herbivores. And picking between those three is tough. So when the Ornithoscelida paper came out, and again, that's an old name, that name dates from like around 1900. But when the recent paper came out, inevitably it got a backlash. People go, no, that can't be right. No, you're not overturning 120 years of dinosaur phylogeny orthodoxy. And there was a paper came out by a bunch of researchers basically writing a response, a literal response, as in we're just talking about your paper, we're not talking about another big bit of science. And they said, well, you've got this coding wrong, and actually that animal looks more like this, and you should have included this one. All very standard stuff for these kind of big analyses, because there's a limit to what you can see, and human error creeps in, and there is some subjectivity, and yada, yada, yada. And their analysis basically collapsed everything, so it didn't actually give you a very different resolution.
It just said it's all nonsense.
So they said, we think you're wrong, but also it's not like they got a traditional Saurisia-Ornithischia split either. And a couple more analyses since then, it's flickering around, basically.
Can we talk about the pelvis thing again? This is what I understand. Okay, so you've got the Saurisia, which... Shush. So somewhere in like the early to mid Triassic, you had a split between two different types of what we would look at and sort of say, oh, they're a bit sort of human-like dinosaur, like, you know, up on their 2 feet type thing. And they've got two different types of pelvis. They split them. And one of them looks like a modern bird pelvis, which is higher up and doesn't dangle down as much. That's right, isn't it?
Well, it points backwards, really.
It points backwards. And then the Saurisia, so that's the Ornithischia, because it looks like a bird. And then the Saurisia have a big, sort of like much more, what I'd call like a human hippie bone, and it points forwards.
Yeah, that's the pubis in particular. The pubis points forward in a Saurisian, and it points backwards in an Ornithischia.
And the Ornithischia go on, and they make Stegosaurus and Ankylosaurus and
Pachycephalosaurs and the Hadrosaurs and
Ceratopia, and they make the Ornithopods. Ornithopods, there you go, like Iguanodon.
Hadrosaurs and Iguanodonts.
Yes, okay, so I'm guessing the right thing. So, but they've all got this sort of weird, what we would call bird-like pelvis.
Yeah.
But then the Saurisia, they go on to create the sauropods, they create...
the theropods.
Yeah, the theropods. Theropodia. But that includes birds, so at some point that pelvis changes back to an ornithischian type of...
Yeah, it does.
But pelvis. So why couldn't the ornithischians? Why couldn't the sauropods be part of the ornithischian and be like birds and transfer? Do you know what I mean? Why couldn't they
Why didn't the pelvis evolve in those groups?
Yeah.
I don't think I know.
No,
I'm not sure anyone does.
But couldn't it have been that the early Sauropodia might have had an ornithischian pelvis that then moved forward again that we haven't found, and that would explain why they're in the wrong group? So the
ancestral condition is Saurisian. If you look at the Dinosauromorphs and Dinosauriforms and other things and earlier reptiles, they would have a Saurisian pelvis. They would have a reptile pelvis.
Okay.
So the derived condition, the change away from the ancestor, is the ornithischian pelvis. So the ornithischians are the weird ones.
Okay.
So think of it in terms of our hairiness as humans.
Oh, yes.
If you go deep into time, those animals didn't have hair. But mammals ancestrally have hair, and all mammals since have had hair, except a very few rare ones like whales that have got rid of it, and us who are in the process of getting rid of it.
We've got it on our heads to protect ourselves from the sun.
Right, and a few other bits. And eyebrows are really useful for getting rid of rain. So yes. An old friend of mine has alopecia, and he doesn't even have eyebrows. On an old forum we used to run for kids asking scientists questions, someone said, what use are eyebrows? And he said, I have real trouble seeing in the rain.
Yeah. And also sweaty, when you get really sweaty.
Yeah. And similar, it's like, okay, we do use them to communicate quite a bit, but that, you can see, that would be a major evolutionary disadvantage if early hominids got rid of eyebrows. Like, anytime you get hot and sweaty or it rains, you can't see. That's kind of a problem on the, on the plains of Africa, where lions can see perfectly well when it's a bit wet, and you can't see a bloody thing. So I can see the point of that. But yeah, so it's the ornithischian pelvis is the derived condition, and as therefore it is also in birds, and it's what we'd therefore say convergent. They have independently acquired that characteristic.
Okay.
But the interesting thing about Ornithoscelida, and this is a classic problem with these kinds of things, is it solves some problems whilst immediately causing a bunch of others.
Yeah.
So one big problem we have with the standard Saurisian Ornithischian split is that actually there are no Triassic Ornithischians. There's a bunch which have been claimed to be, and then are often either controversial or turn out to be misdated or yada yada yada. So the earliest definitive Ornithischians we have are in the Jurassic. There may be one Triassic one, but if there is, it's like right at the end, when dinosaurs have been around for tens of millions of years at this point. Now, if there's an evolutionary split, which gives us the Sauropodomorphs and Theropods on one side and the Ornithischians on the other, and there are sauropods sauropods and theropods running around, by definition, the ornithischians must exist. The evolutionary split has already occurred. So where the bloody hell are they? Because we've never found them in a good 150 years of digging.
And the sauropods that we found and the protosauropods we found.
Yeah, there's loads of sauropodomorphs in the Triassic. Absolutely everywhere. And loads of theropods absolutely everywhere. We never find ornithischians, even though they're supposedly about. So one answer to that question would be...
They didn't exist.
They haven't actually split yet.
Yeah.
Right, and they're part of this stem theropod group. So the reason we haven't found them is they haven't actually split.
Oh, wow.
The Ornithoscelida idea largely solves the problem of where are the missing ornithischians, and it makes the feather evolution thing a bit more simple, because we do have a bunch of filaments in various early ornithischians, and we know we've got filaments all over the theropods, but never in the sauropodomorphs. So if the ornithischian theropods go together, well, feathers evolved once and then was in their descendants, and then that's why you never see it in sauropodomorphs.
So there's actually a split, in this sense, there'll be a split from sauropods and theropods, and then a split in the theropods to ornithischians.
That's what I think is the implication of that. That's not quite what they recovered, but I think that's the implication, is that ornithischia are a bit more... They're not right at the base of theropods, and the two basically split simultaneously. I suspect it's that they came a bit later. But the Ornithoscelida then causes other problems, because we know that the theropods are extremely pneumatic all the way down to their origins, and the sauropods are very pneumatic, but even their forerunners, the prosauropods, they're not as extreme, but there's good evidence of pneumaticity going on. And then absolutely nothing in the ornithischians ever. So you're like... Well, okay, so what the hell's going on with the pneumaticity then? So did that evolve twice separately in the theropods and the sauropods, and then was lost in the ornithischians? That's weird, because we generally consider pneumaticity to be a fairly major advantage. And if it was present in pterosaurs, which it may well have been, that implies the ornithischians lost it, even though they're well within a really highly derived pneumatic group.
But if you think about it, wasn't one of the early ornithischians a stegosaurus?
Stegosaurs are fairly early. There's a big group that come before them called the heterodontosaurs.
Okay, but are they similar in that they're very sort of, they're ankylosaur-like? Because ankylosaurs come off stegosaurs roughly.
They're very close, yeah.
Yeah. So, and I'm thinking that they're very heavy-set animals. So surely...
Well, I know where you're going. So no, for two reasons. First of all, if you are that heavy, wouldn't it be a pretty big advantage if you could cut your weight down and get rid of a whole bunch of bone?
Not if people are trying to flip you over and eat your tummy.
Well, that's for the Cretaceous ones possibly, but not necessarily in the Triassic not necessarily in the Jurassic. Yeah. And secondly, the heterodontosaurs are really small. A big heterodontosaur is a meter and a half long. It's a little running around on its back legs guy. So yeah, the Ornithoscelida idea, even if it's right, sorry, that sounds a bit. Oh, I don't think. If it is correct, it does resolve a couple of issues, but it immediately opens up a couple of others.
Which is why are iguanodons so chunky?
Yes, among others. But it's that thing. It's like, the current Saurisia Ornithischia split, we have a big problem of where the bloody hell are the Triassic Ornithischians. We can arguably solve that with Ornithoscelida and then immediately turn up the problems of, well, what the hell's going on with the pneumaticity?
So we still really haven't sorted it totally. We kind of have, but we kind of haven't.
No, but it's definitely coming, though, because in the last 10 years, we've had so many more of these pre-dinosaurs. So, the dinosauromorphs and the dinosauriforms. So the animals which will give us, the understanding of what's going on inside. Lots more species, lots more skeletons, lots more different places. So they're turning up in Ecuador, they're turning up in Tanzania. Brazil and Argentina have already been a hotspot for them, but we're getting more there. That is inevitably going to help resolve this. And the data sets just get bigger. And as you find more bones and as you find more species and as you realise there are more characters or better way of dividing things up, you get a better and better idea of how you pull things together. And we're finding lots more stuff just kind of over the line. So we haven't really, I've been deliberately avoiding them. There's a group called the Herrera Saurus. So Herrera Saurus is this little carnivore from Argentina, 2 and a bit meters long.
So it's carnivore, so it's sauropod type thing.
Well, this is where we're going. So Herrera Saurus, it looks like an early theropod, and when it was dug up, it was described as an early theropod. And if you just looked at a skeleton, you'd go, yeah, it's a theropod with a fairly chunky head, which is probably what you'd expect from a really early example. And it's come in various analysis. It's been the earliest dinosaur, or just outside of Dinosauria, or the earliest theropod, or in the Ornithoscelida analysis, it comes out basically as its own little group, or Herrera Saurus plus a few others. And you've effectively got 4 groups: sauropods, theropods, ornithischians, and Herrera Saurus. But the Herrera Saurus is like 5 of them, so that's why I kind of skimmed over it. But they're dotting all over the place. And similarly, we've got things like Eoraptor. And you might guess from the name Eoraptor that people thought it was an early carnivore, the early hunter. Our best guess now is actually it's an early sauropodomorph. But it's got carnivorous teeth, which is what you'd expect. Again, all the early dinosauromorphs and dinosauriforms were carnivorous. If the sauropodomorphs are all herbivorous, then at some point they've transitioned from one to the other. It's not a surprise that you would get some kind of carnivore or omnivore at that base. But again, it shows you that there's an animal floating around that we originally said was a theropod, and now we say is a sauropod. And this is the problem with these very bases, because they haven't differentiated yet. The characters that make it obviously a sauropodomorph aren't there, and the characters that make theropods totally different aren't there. And some characters will come and go repeatedly because, you know, evolution's changing quite a lot as a big group evolves.
If you've ever looked at the back leg of like a possum, if you looked at its back feet look like human hands. They just look like a human hand, and it's really freaky, and you're just like, how did that get there? Somebody must have chopped it off and stuck it on.
Yeah.
If things are evolving repeatedly, so say for whatever reason pneumaticity is actually quite a quick evolutionary jump for whatever reason, then you're completely mucked up.
It's the same with filaments. You know, maybe the evolutionary pathway through the developmental changes to make a filament out of a scale is inverted commas easy. Like, one protein shift somewhere can turn a scale into a filament, and therefore a single evolutionary change, a single mutation could produce that. Let's just assume that's true.
Get a fluffy fish.
If so, then getting filaments on pterosaurs and filaments on 2 different groups of ornithischians, which are actually quite well separated, the ceratopsians and the very early heterodontosaurs, and in theropods, could have easily happened multiple times convergently.
Yeah.
A parallel one that I give my students is spininess in mammals. So we all know that hedgehogs are spiky. Well, so are porcupines, but those animals are very different groups from each other.
And echidna.
And then you've got echidnas. And then there's the spiny mice. And then there's the tenrecs in Madagascar. There's 5 different mammal groups, all of whom have shifted their fur into spines, more or less the same way, entirely independently of one another. If there's a similar thing going on with converting a scale into a filament, there is no particular reason to think that the ornithischians should go with the theropods because of their filamentousness. And also, therefore, we probably shouldn't call heterodontosaur filaments feathers, because they're not. They're an evolutionary separate thing.
Oh, no.
But we don't know, which is why it'd be very useful to know where the bloody hell the ornithischians go and what the hell they actually are. And if someone could turn up a Triassic one, that'd be great.
So, really, the earliest ornithischians are in the early Jurassic?
I think so, yeah.
Wow.
Because I really don't do early ornithischians. I've got a horrible nagging feeling at the back of my head there's like one from the end of the Triassic. But in general, there are lots and lots of Saurisians and sauropodomorph dinosaurs and the earliest sauropods and all kinds of different theropods running around in the Triassic, and the ornithischians are nowhere to be seen.
That's really weird.
But some groups just do that. If you looked at the modern world now and went, oh yeah, the platypus, that's closely related to...
Quack, quack.
Right. It's got this enormous evolutionary gap between itself and everything else, and its fossil record is very sparse. It is possible for groups to hang around for enormously extended periods of time and not show up in the fossil record. It's perfectly plausible that ornithischians evolved Middle Triassic, some little isolated series of islands or some isolated...
rocky deserts and cliffs.
Right, or they were just in Russia where we've got, northwestern Russia where we've got no
data.
Triassic rocks at all, etc. And so they hung around there quite happily for 50 million years and then the environment changed and they went ballistic. But it's, that's a just so story that we can say, and it seems unlikely that there is so much success in the other dinosaur groups and not them.
So before dinosaurs, because have we got anything from, what... I don't know, other than, obviously I know about coelacanths, which are still around today and were back way before.
Okay, well, yeah, there's a really good example, of something that was knocking around forever.
I know, because everybody thought the coelacanth was extinct, and then some bloke fished one out of the sea and went, oh. Anyway.
Well, they found it in a market.
So somebody was eating them.
No, well, they are still rare and not caught very often. And it was an ichthyologist, basically, in a African market. And, here's the fishermen have pulled their stuff up. And, generally the story is jaw hit the floor, bought the damn thing, and went, these have been extinct for 70 million years. I just bought one off this guy, which you'd hope went through, the normal, Monty Python-like negotiation. It's like, oh my God, I've just made the greatest discovery of my career. How much do you want for it? 500. Give you 150. 400. 250. You got to barter.
That's amazing.
For your discovery.
So,
anyway.
Okay,
sorry,
if we're going back in time, before the Cretaceous, you have the Jurassic. Before the Jurassic, you have the Triassic. Before the Triassic, you have the
Permian.
Before that, I don't know. Before that, I don't know. Before that, don't you have, the Devon one?
Devonian.
Yeah, you go all the way back and you end up in Devon. And before that, presumably, is Cornwall.
Yes, because I did purely a zoology degree. To this day, I am shamefully bad at my geological periods outside of the Mesozoic that I work on. And I'm not great at the Mesozoic. All the subdivisions, the Maastrichtian, the Campanian... Oh, I can always remember those two, and after
fair
that,
enough.
When's the Oxfordian? It's sometime in the Jurassic. I can't remember if it's early, middle, or late, let alone the numbers attached to it. And then, Carboniferous, Cambrian, Precambrian, Permian, Devonian. Oh, I'm awful. Anyway, so we got those periods.
It's just how long has life been around for, really?
So the Earth's give or take 4.5 billion years old.
Yeah.
And life is 3.5 billion-ish, with lots of caveats attached to that.
I mean, dinosaurs are really recent then, because we're talking 250, I think it's the earliest Triassic bit. So they're 200, what did you say? They were 200, well, they're roughly.
The oldest kind of definitive dinosaur is about 220, 225. The odds are they're older than that, because the odds that you found...
The first one.
is basically nil. And early groups are going to be small and low in number and, hard to find. But it's probably not going to be another 50 million years. It's probably going to be another 5 or 10. So, 250 at the absolute massive outside.
Right.
And then to 66. So,
yeah,
well under 200 million years. Probably more like 160. That's a good chunk of time, but again, against 4-point-something billion, it's also not that much either.
Yeah, it's really not. And
this is why the fact that sharks have been around being pretty sharky since before trees. Now, there's a group who knew what they were doing. Yeah, there were sharks before there were trees.
That's incredible, isn't it? There's also, but isn't the part of the reason we got coal because all the trees, there was nothing that ate the rotting trees, and so you've got these layers of trees.
At least partly, yeah. It's the Carboniferous because it's for carbon. Because you had just trees and trees and trees and trees and trees.
And they just died and fell on top of themselves. And
lots of forest fires. That's why they're carbon and partially charcoal. And then that's been suggested to be linked to the fact that if you have a forest-covered Earth, you're jacking the oxygen percentage up quite high, which makes forest fires a bit more likely.
Well, so it balances out in the sorts of...
Yes.
Yeah.
And now a geologist is immediately going to comment, that's nonsense, Dave. That's what they used to say in the 60s. Well, that's the last time I read any of those.
That's the last book you read on geology.
Yeah.
Well, I tell you who knows even less about dinosaurs.
Woohoo! That's what we need.
That Dave does about geology. And that is Professor Sophie Scott. And she can ask Dave a question. Professor Sophie Scott, thank you very much for coming on Terrible Lizards. Do you have do you like dinosaurs? What's your background with dinosaurs? Are you interested in them? Have you ever been?
Yes. When I was a little girl, I was a real kind of hardcore biology nerd, and I was quite obsessed with just the sort of timescale of biology, and that meant I was very, very interested in dinosaurs dinosaurs because also they're brilliant. But just sort of thinking about how, evolution and this, like the scale of things where there could have been a whole world of these creatures that, I know birds are dinosaurs.
That's more than a lot of people do. You already are ahead.
And it just seemed really sort of amazing. I mean, I think if I could just get in a time machine, I probably would. I know I'd be almost immediately eaten, but I would, before I was eaten, I'd be really interested in just seeing what was it like? What would it possibly have been like? I find it endlessly fascinating to imagine. I'm very interested in, my area of research is sound and communication and human brains. And actually, sound is a very interesting form of communication, and it's very widespread. Like on Earth now, it's a very common way of, sending distress messages, all sorts of things. When you want something to go quickly, you make a sound. And I just wondered if we knew anything about what dinosaurs sounded like and what sort of sounds they could make.
We know a bit, but inevitably not much. So the short version is they're probably not doing anything like many birds do. They don't have the tracheal system to do all the funky noises that lots of stuff do. And they're more like, chickens and ducks that go bang and, make
yeah.
Right, but not very complicated noises. And then, crocodiles and alligators actually make far more noises and more complicated sounds than a lot of people realise. So it's not that they were limited to simple grunts. They would have been almost certainly some variety. And of course, again, we've got 1,500 species across 150 million years. Some of them were doing something weird that we'll never know about. But, our baseline assumption is that most of them had a fairly narrow repertoire of sounds that they could make. But beyond what I think a lot of people would probably guess, they can make some grunts and squeals and rows and stuff. But going on to the neuroanatomy side of it, or at least not quite to the neuroanatomy side, when we get really well-preserved skulls, we do still get bits of the inner ear preserved. And so if you 3D scan them, you can look at what frequencies those hollows are relatively attuned to, which I think is a classic example of where you could be dangerously misled by that evidence as to what it tells you, but it's still fascinating nonetheless. So, I mean, I can imagine, if you find a mid-sized animal and found that it was attuned to, say, low frequencies, it would be easy to make the argument, they're communicating with low-frequency sounds.
Barry White.
And, of course, an alternative interpretation is they're predated on by animals that make low-frequency sounds, or big, heavy predators tend to make thumps on the ground when they walk, and that's what they're most interested in. And so it's completely the opposite of what you think. But even so, I think it's a great example of one of those, oh my God, you can work out what sounds they could hear. It's like, vaguely, but that's kind of amazing for animals that have been dead anything up to 225 million years ago. And we're like, yeah, actually, that one's quite good at high frequency, and that one's quite good at low frequency. And that one's got a big, oral processing lobe on the brain, so actually it's probably doing something quite clever with it. I think that's a good example that goes well beyond what most people would think that we as scientists can pull out of that data. Or that data would ever be available.
Aren't there some ornithischian types with that massive horn that they think was for blowing out of? I can't remember their names.
So the hadrosaurs.
Yes.
So some of the duck-billed dinosaurs have these giant crests on the head which do connect to the nasal passages. And those, it would be a big surprise if they weren't making big noises through them, because they look really well suited for it. And it would be a very big surprise if this wasn't an important part of their communication repertoire. Though probably more about sex than what elephants make lots of deep low noises, but that's about communication between all kinds of different elephants. This is almost certainly much more about hey kind of or oi kind of noises.
I've always been very struck, if you look at mammals, because there's so many different ways that you can make sound. Like in nature, there's lots of different things you could do, and sound it's very low energy. It's quite an easy way of doing much easier than making light appear, for example.
Well, and it's unidirectional. That's the thing, for visual signals, you have to be looking at the thing that's trying to communicate with you. And smell lingers, but it also dissipates. And sound has this phenomenal property that you can stand somewhere and make a noise. And if your noise reaches a kilometre, anyone in a kilometre radius will automatically hear you. And that's handy when you want to let someone know something.
And it's certainly, so if you look at mammal vocalizations, which are made with the larynx, and the larynx just evolved to stop things falling into the lungs. It's just a structure for protection. And all mammals pretty much much have found a way of bringing those, the larynx together and blowing air out through it, even if you're just breathing out, and making a sound that way. And then even then that's pretty basic, but if you look at something like the red deer, they, a bit like your hornbills, all sorts of pretty complex stuff on top of that. You don't have to have a really amazing set of articulators to still do, pretty sophisticated things with that noise.
Yeah, it's really cool. I mean, so my outstanding memory of noise, which in mammals, which I love telling this story. So I was in Pittsburgh, so ironically with Mike Peep, who we mentioned earlier, when he was working in Pittsburgh, and they had African elephants, which is obviously quite unusual. Most zoos keep the Asian ones, and there was a relatively young calf. And so the bull elephant had basically been penned off from the rest of the group because clearly they were concerned that, he might get a bit tetchy and, don't want an accident happening. And so the females and the calves were running around outside and the male was locked in. And they had a system in there, so he came in and out different times. But right now he's inside. And this is, it's an elephant house for African elephants. The walls are feet thick of concrete and there's steel bars everywhere. And it's absolutely massive. It's a block of flat-sized buildings, all of which is relevant because he was doing that big, deep elephant rumble. And I realised I could feel it. And I put my hand on the wall and the wall was vibrating almost visibly. And you're like, this is 1,000 tons of concrete, 10,000 tons of concrete. I mean, I wouldn't want to estimate, but it was a lot because it's a big effort. It's a big house for 10 elephants, of course. And the whole building was just shaking. Yeah. And he was just standing and wasn't doing anything else. It's not like he was pent up with rage and running around this huge activity. It was clearly no effort for him to release this rumble, which was shaking the building.
I know people who snore like that.
Yes.
Yeah. Oh, so do I. But it's like, and then you go, right, some of the big sauropods were 70, 80 tons. If a 4-ton elephant can do this, oh boy.
Yeah.
What might they have been capable of?
I would love to have heard that.
Oh, wouldn't you? And imagine if it's a couple of dozen of them together doing it. Oh, right, but take it to an extreme with a nice salt pan or not salt pan, but something with really hard flat rock. Brilliant for conducting sound. And you've got a herd of 30 or 40 animals at 60, 70 tons plus, all doing this. I doubt you could stand up. Think about what that must be doing. It would be deafening for starters. Yeah, water would be,
fizzing,
jumping, but you'd hear this from tens of miles plus. I think the record for elephants is certainly, multiple miles, double digits. And then think about what this might be able to do. I wouldn't even want to guess, let alone try and calculate it. But boy, it's going to be impressive.
It would be extraordinary. The other thing I'm always kind of struck by with the evolution of hearing and sound in mammals, and obviously I'm going to keep talking about mammals because they're the ones I work with, but because of the way that the mammalian ear, which is again highly conserved, the elephant ears are basically just the same as your ears, just different size. We have these 3 little bones inside our ear for transducing the sound vibrations through to the inner ear. And am I right in reptiles it's only 1?
Yeah, pretty much. I'm going to have to say right now, I really don't know because I never look at this stuff. I genuinely can't remember what it is in reptiles. That sounds right.
I think because mammals have got 1 jawbone and reptiles have got multiple. Oh,
they've got loads. So,
and we've kind of adapted those lizard jawbones into mammal ears. Yeah, that's where the extra bits come from.
So the 3 ear bones in mammals is absolutely the back of the lower reptilian jaw. It's not all of it. So reptiles have a whole suite of bones in the lower jaw. It's not just those 3 and the dentary, which holds the teeth. There's 6, 7 each side, I want to say. But yeah, those have absolutely migrated off and come up inside the ear and allowed that. It's a wonderful evolutionary story, and there's some really good fossils that show the various transitions and the way that it shrinks and frees up and moves and then turns inside and does other things.
The thing that really struck me, and I only found this out a couple of years ago, is that gave mammals a whole range of frequencies that reptiles can't hear.
That wouldn't surprise me, no.
So So it's, if you think about it, and it goes in really wide. So like mammals go really, really high and really, really low, like the elephants.
Yeah.
All reptile hearing, including birds, cuts off at 10K. And so it doesn't matter how big you are or how small you are, that's when your hearing stops. And that's why we can hear the sounds birds make. We can't hear mice.
Oh, because they're forced into our repertoire.
Well, no, because they're making sounds they can hear, and
we can hear more than they can.
Yeah, so you can't normally hear, fortunately, rats and mice, but we can hear them, and I thought, of course, it's always when you think about it, and it's almost like sound, this wider range of sound kind of opened up all these different possibilities for mammals. So that's why you get like bats and echolocation, because they're right up at the top end.
So the first thing I'm thinking of is, what about the cave swiftlets, which echolocate?
Yeah.
But then at least some echolocation you can do at
exactly
relatively low frequencies, which is why we can still hear bats.
Exactly. It doesn't have to go high.
No, so I'm now immediately and there's that whole suite of people with sight disability who learn to echolocate.
Effectively, if you ever get a chance, if things are ever normal again and you're ever in London, I will take you to, we have an anechoic chamber, which is, it's sound absorbing. It's horrible because it has no echoes.
Yeah, I've heard they really freak people out because you can't even hear your like heartbeat kind of stuff.
But also, if you make a sound, you are getting echo information, and actually you do use it. You don't realise you're using it because you've got sight normally, but it's part of your kind of feeling in the space. And as soon as that's gone away, I mean, it makes me feel actually sick. It makes me feel like somebody's wrapped a bag around my head that I can't see, and I've been forced into some sort of tight thing that's completely occluded my hearing, although I can still hear because the echoes aren't there.
So all you need to do now is get a few cans of Black 2.0 so that there's no light.
Yes. Whoa. Some people love it. I have like colleagues who are like, I go and spend time there.
I know about them, and I would love to experience it, but I suspect I really wouldn't like it. That doesn't mean I don't want to try.
You let me know when you're next around and things are normal, because it's.
Well, I am in London.
Well,
I just don't leave my house very much.
Let's get left. You're in London. Let's find out when things are normal then. Yeah.
To be fair, there's probably no one in it.
No, it's true. It's true. Although one of my colleagues did get trapped in it. It didn't.
Oh, no.
It didn't used to have. It didn't used to have a handle on the inside.
Did no one hear him when he yelled?
Exactly. He got left in it, and then he had to tear the ceiling to pieces to kind of get a piece of metal off that he could then use to lever the door open. Otherwise, he would have just died in there. Because again, literally, no one's going to hear you.
No one can hear you. Oh my God!
And when we replaced the door, we put a handle on the inside. So.
I mean, it's not the same thing, but in my department, we have huge problems with the lifts, and they keep breaking down. And a couple of years ago, famously, the lift broke down with the engineer in it who'd been sent to fix the lift. And I believe they had to call out a second engineer to get the first engineer out, which tells you everything about how good our lifts are. It's not quite the same.
No, that's beautiful. That's beautiful.
It's the same general principle of... But where did anyone last see him? Well, he went to fix a lift.
So then, here lies the question of what dinosaur would you most like to hear, both of you?
For me, it would be something like a Parasaurolophus. You know, they're famous for this, and they've got such a big thing, and it must be sound generating. And yeah, I'd just love to see a herd of them going nuts at each other.
Yeah.
And just see if that's really... I'm sure it's one of those things, I'm so sure it's true, and yet it's really hard to prove.
They could have just been sneezing the entire time. That could have been it. It could have just been a massive sneeze.
It's a massive sinus infection which got out of control. 7 million years later. They consist entirely of head.
No, I agree. That would be a thing to hear.
Oh, I want to hear the sauropod stomps and the rumbling. Sauropod snoring. There you go. Would be. I mean, that would be interesting.
Yeah.
So, did we answer your question, Sophie?
You did. I've always because you get so many parallel aspects of things that you find. Often you think, only humans do this, and then you find versions of them in birds. They are always the sort of the best examples of where you find particularly for aspects of like, you know, vocal imitation and stuff like that. And it's really I've always wondered what that would mean for dinosaurs, because birds obviously aren't one set. It does vary across birds, but I've always wondered what it would mean.
Yeah, it's a shame there's really nothing to suggest that any of them produce the mimicry that you get in parrots or lyrebirds, or actually even magpies are supposed to be really quite good mimics if they get the
ravens are.
Yep.
Ravens are amazing.
So yeah, unfortunately none of that, because that would be great fun if you had Polywana Cracker coming out of some 8-ton behemoth. But
it's like all this stuff I really care about, like tongues and larynxes and brains, doesn't fossilise, so that's it.
But we get bits, because we get the hyoids and the tongue supporting bones, and they don't preserve very often, and they have limited information because the hyoids vary way more than the tongues probably did. But still, it's not that we know nothing. And I always think this kind of stuff's frustrating, actually, because if we didn't know at all, we'd go, well, we don't know, but we know just enough that we know we don't know. It's like, it's on the edge of understanding, but not actually good enough, just there to tantalise and annoy.
Beauty of science.
Yeah, we'll call it that.
Well, thank you so much. Is there anything you would like us to plug?
If people are remotely interested, I have a podcast, like everybody, I know this, but called The Neuromantics, nice. With a poet.
Nice. Your eyeliner really doesn't
exactly.
do that
It's I wanted to have pictures of us like with headbands and crimped hair. It's me and the poet Will Eves, and he gives me a poem or a book chapter or a book to read, and I give him a scientific paper to read, and then we try and make sense.
Oh, nice.
Of that. But feel free.
Ruin art for everyone.
Exactly, absolutely. Yeah. I will not stop.
Ruin art and science.
I will not stop until I've done that. Yeah.
I do hope that T-Rex cheeped.
Yeah, even if it's just the babies, that would be very nice.
Yeah, little chicks. Just go cheep, cheep.
Yeah, I mean, you can get some entertainingly plaintive, small, whiny noises from surprisingly big animals.
Particularly people over data sets make those incredibly small, whiny noises quite a lot if they're trying to get their programs to run. Whatever we decide about who's related to what, I just know sauropods are just can't be related to T-Rex that closely, surely. Why? Hurts my brain.
That's the kind of in-depth analysis that got us where we are today.
Exactly. I don't like it. It must be wrong. There you go. Emotionally, what happened is a little ankylosaur stretched its neck one day to try and reach leaves, and got bigger and reached more. And yeah, Just So stories are much better at this.
So we're now into Lamarckian evolution as well. It's the neck stretching which is producing long-necked animals.
Okay, until next episode is your questions. I think we've collected enough questions for that episode, but so just in case, you could always email us, terriblelizardspod@gmail.com. Do please, and do remember, if you were wishing that we'd done the strangest sauropods, even though we've only got like one skull to cover all of them. But if you wanted to vote for that and you're really thinking, why did I have to learn all of this stuff when we could have been stomping around, hoovering up food? Well, you should have become a patron. So please visit patreon.com/terriblelizards. You will find us, and you can give us, basically do the equivalent of buying us a coffee, and we will try and get more episodes out to you sooner. And more support we have, the more likely we are to do that. So thank you very much, and until next week, rawr. Thank you for listening to the Terrible Lizards podcast with Izzy Lawrence and Dr. Dave Hone. This episode was only made possible thanks to our patrons on Patreon, and for listeners like you who share our content with your friends. So please spread the word on social media. You can find us on Patreon, Facebook, and at ISZI_LAWRENCE and at DAVE_HONE on Twitter. Include the hashtag Terrible Lizards. Ask us your questions via terriblelizards.co.uk, email terriblelizardspod@gmail.com. We are hoping to bring you so much more, but we can only do that if our audience continues to grow. So please like, share and subscribe.